Hello and welcome to the Queermonger Institute, our Q&A Conversation for Exploration series. I'm Paul Robert, the Executive Director and President of the Institute, along with my wife, Laura Lee, the Director of Research, Education, and Outreach, and of course, on behalf of our Board of Directors, our advisors, our volunteers, and supporting members, we want to thank you for joining us today. The Queermonger Institute, it's an independent, nonprofit research organization committed to researching consciousness and the human experience, following the footsteps of our founder, anthropologist Dr. Felicitas Goodman. And as an educational institution, we take an open approach and we invite scholars in related fields to help broaden the scope of our own work in exploration. That's why we call this Conversation for Exploration. On these weekly Sunday discussions, we've had a full spectrum of topics: neuroscience, anthropology, archaeoastronomy, ecology, philosophy, shamanism, hero's journey, roots of theater. It goes on so much more, basically from the arts to the sciences and everything in between. And you're welcome to visit our website at queermongerinstitute.com. All of our presentations are free. And it's a nonprofit. We invite you to become a supporting member, and we thank you, the community members, who continue to support the mission of the Queermonger Institute. Today, we're going to be sharing some of the latest images and discoveries from the James Webb Space Telescope. The images are breathtaking, and the discoveries, they're hugely significant. We live in a remarkable time of technology. It was just like 100 years ago that we didn't even know that there was galaxies outside of our own. Now we estimate there are trillions. And what will be the discoveries from these exoplanets, these planets beyond our own solar system? What would that tell us? For the foreseeable future, the James Webb will be taking us on a journey of breathtaking discoveries through space and time. And you notice that I said space and time, because the Webb telescope is like a cosmic time machine. Looking out into space is like looking back into time. And by tracking how light travels through space, we can see the very start of the universe itself. The James Webb Telescope is a huge step in searching also for alien life. And I found this fun quote recently in a Forbes magazine article. Here's what they had to say.
Okay.
It says, "Of course, if Webb was ever to point at a planet and see signs of alien megastructures reminiscent of a Death Star or a fleet of advanced spacecrafts, we'd have to have some serious discussions as a species. So in a way, you might also consider the Webb telescope a sort of an early warning system."
From science fiction to science fact.
Exactly.
Yeah.
So anyway, all of this ties into us as an organization, the mission, continuing to bridge that spectrum of the human experience from the inner to the outer technology.
Well, you know, I just want to recognize the impact of this work.
Okay.
This international and worldwide community of astronomers and engineers and scientists. And we feel so privileged. We feel so honored that 3 of them are here with us today. And that it's been such a beautiful bookend. Our 3 guests, all astronomers and physicists, looked at the James Webb Space Telescope right before it's launched, showed us what it was going to do, what its significance was, its technology, all the really myriad tasks that went into it. And here they are back again, because now it has successfully deployed, sitting there a million miles away, and it is bringing back some of the first images. And so we're going to look at those and just really celebrate this accomplishment. We have with us today physicist Bob Woodruff, aka Woody. I am told he is the world's most recognized designer of telescopes and optical instruments in space. I mean, wow, Woody, what an accomplishment. He notably helped design the Hubble and its famous fix, and that is part of the story that he told us in that previous interview. We want to thank Tony Hull. Tony put this together. These are all Tony's colleagues and friends that join us today. And Tony is a astronomer and physicist at the University of New Mexico, Department of Physics and Astronomy. He's played many, many roles in space, and continuing to help develop many of the missions. He's a mission architect. He's helping to design and talk about missions all over. About to embark to Europe to continue the conversations. It's a competitive field. And he spent over 5 years directing the team that polished the mirrors, the mini mirrors of the James Webb. And his colleague is Diana Dragomir, again at the University of New Mexico, Department of Physics and Astronomy. And Diana specializes in astrobiology. And so this is huge impact. What is that data going to tell us about those many worlds where there might be life elsewhere? And already they're finding more and more exoplanets already. So, So thank you all for being back once again. So Tony, this is the team that you pulled together. Fill in the blanks of the accomplishments of you and your colleagues. Set the stage for us. Yeah.
Okay. Yes, I'm happy to do that. It's it's really an exciting journey. And first of all, I want to say that I love this format that we have here, in that we can bridge worlds. We can look at things from an intuitive point of view, from what happened and what the impact is, as well as the nuts and bolts of how we make things happen and the rigors of testing the concepts that we have. So it's really very exciting to be able to talk in this way between two worlds. There are very few formats that allow us to do this. And we're just happy to do that. Paul and Laura, my hat off to you both. It's a wonderful format. So I guess I'd like to just say a few things to begin with. And of course, it's absolutely wonderful to work with Woody. He and I have worked together for a couple of decades. And I recognize him as a person of huge achievement who always gets it right. And that's rare, but it's wonderful working with him. We are developing a mission to this day, which is something going forward, and we could probably talk about it. No, we probably won't talk about it today, but that's fine. It's also been wonderful working with Diana. I've gotten to know her some over the last year or so, and it's really, I have exoplanets in my background. I'm not doing that now, but to have somebody on the faculty of the university who is so much at the core of these explorations, that was part of my world 25 years ago. It's a wonderful thing. And Diana has just really wonderful, fresh ways of looking at things. And of course, she is addressing one of the big questions, and that is that of exobiology. Well, let me step back for a second, and I want to talk a little bit about missions and the phases.
Well, before you do that, I want to just say hello to Diana, have a few words from her, and from Woody, if I could.
Of course.
Hi. Yeah, I'm happy to be here again.
And what does it mean that the James Webb is successfully deployed and bringing data in? What is that?
Is that from you or Woody?
Yep.
With you first.
Sure, I can go first. So, well, it's funny because I was on a personal trip in Italy when I saw the first images from James Webb, and I was on a train. And so it was a little bit, I don't think I had to get off anytime soon. So that's good, because otherwise I would have possibly missed my station. But it was, I mean, I just kind of sat there, and I wasn't sure for a moment if I was looking at real images or artists' conceptions that NASA used to use a lot to illustrate in more detail than we can see with telescopes some of these astronomical objects. And then, I kind of did a bit of research just to be sure. And indeed, these were real James Webb images, and I was just blown away. And since then, I mean, it's been 2 months, and there's so many new images and some really cool science results that I'll be telling you a little bit about.
And you and Tony have been speaking around the country on this. We had to wait our turn.
Virtually. Well, Tony more, I kind of mostly just sat here, but through the computer screen, you can get pretty far.
Yeah, thank you. And welcome back, Woody. It's so good to have you here. And
it's good to be here.
You worked on so many of these telescopes. So tell us about the emotional impact for you of seeing this. You helped pull this off. Yeah.
It's really good to be here. it takes a long time from first initiation to the design to final deployment. And this one slipped and slipped and slipped, which is normal. It took about 25 years from when I first did the design to when the thing flew. And it had a whole lot of single point failures, a whole lot of things that if it didn't go right, it would not go right. And I was pleased to see how good the people who built it and engineered it, how good they really did. They did a very, very good job because it deployed. They were able to phase it to make it to get it in alignment and produce stunning images. So
And
very
no possible
satisfying.
fix after the fact, like there was with Hubble. Oh my gosh. Yeah.
Yeah,
Wow.
yeah.
What's the
Very,
story, Tony, that something hit a mirror, a little tiny speck of dust? We didn't expect that. What happened? I mean, how fragile is
Well,
this to keep going?
let me say, yes, everything is fragile. And as Woody will tell you, space is a very challenging environment. There are many things that can happen. And what has happened to Webb, as of 2 weeks ago, I've not checked recently, but there have been 6 micrometeor impacts on the mirrors. This is actually within the models. This is not a surprise to NASA. The effect of micrometeor impact had been predicted, and that's part of the lifetime and the performance budget for Webb. And Webb is particularly vulnerable, of course, because it's so hugely open. The shocker, however, that came out in June was the first impact was at the very large end of the spectrum that was expected. And so this was, it had people spinning and asking all sorts of questions about how we're going to do our next telescope and are we going to do things differently. I'll probably talk about this later, and maybe Woody and Diana will join in on that if we have time about what's next, because there's always a next. But this is part of what happens. We get hit by radiation, electronics get cooked. You have mechanisms that fail, gyros that only go a certain number of years, fuel and cryogens that are expended. So there are a lot of things that happen that limit the lifetime. This is just one of those effects. So it's not a surprise, but I think people were not ready for one of the big ones to hit early on.
When you say big, I mean, what is micrometeor? How tiny piece of dust? I mean, what is out there? And
I think you might think of maybe half the size of a BB, if you know what a BB is. I don't know. I mean, it's something small, but it goes very fast, and that's the downside of it.
Impact. Yeah.
And unlike glass, beryllium is a metal, and it has a certain amount of ductility to it, and that means that if you impact, you create a stress. And as the stress is released, you do not necessarily go back to the exact form you were before. And Woody can tell you a little bit more about what that might do to an optic, but these things happen, and we have to design around them. I personally think the next great telescope will have a tube around it as opposed to being so exposed. But I think it was a little bit risky, but I can talk about that if you like later on, maybe in more detail than
Also,
what
it's
you'd like to
very,
hear.
very cold, and when things are cold, they seem to be a little bit more brittle. But
No, actually, that's not so much a factor on that.
Yeah.
But
You would know. You made those mirrors.
yeah. Well, I made a lot of brilliant mirrors in my day. So well, I'm just going to have part of, again, a brief introduction from my point of view.
Sure.
And we talked about starting the optical design 25 years ago and unraveling this, and we'll go into that in a couple of minutes. But I remember before Hubble was launched, and Woody probably does too, back going to a lecture, I think in 1989, on the large deployable reflector. And I do remember that was the day of view graphs, and some poor person was talking about that. And at that time, you'd have your secretary type up your view graph for you. And the title of each slide was the large deployable reflector.
Horrible.
Anyway, it
deployable.
embarrassed the person, but it's anything but deplorable.
Yeah.
So this soon became, as it got a bit more mature, when Woody got involved, it was called the Next Generation Space Telescope, because Hubble had been launched then. And
There it is.
yeah,
Mhm.
so thank you, Woody. And then eventually, I think about 2002, was it, Woody? It acquired the name of James Webb, who was a NASA administrator. So the first phase was developing the concept and doing all the concept battles, working from a blank sheet of paper, and that's something that Woody did brilliantly, and he'll talk about in just a couple of minutes. And then we go into the implementation stage, and I had the privilege to be a part of that. But let me go to the year 2011. The Office of Management of the Budget announced James Webb Space Telescope was canceled, kaput. It can't be.
Right.
The overruns are too large.
Mhm.
And we're going to teach, this is Congress, we're going to teach NASA and National Science Foundation how to manage the budgets. Well, Woody already mentioned the huge complexity, and great thanks that all the tests and things that were done, all the evaluation, all the stop, let's fix this type of thing. Because as he said, there are many, many failure modes. Any one of them could have killed the telescope, and yet none of them did. So the battle was fought almost immediately. Some members of Congress, including Barbara Mikulski in the Maryland district, went to battle, and backed by the astronomy community, saying, no, this is something we must have. And the implications were not just the loss of Webb, but the implications would be the loss of a great observatory. If this went away, then it might have been decades before NASA implemented another great observatory. And Diana would not have this great instrument to work with, and maybe never in her career. It's a really kind of remarkable thing.
But it seems like it's not just the cost of the telescope, it's really the cost of all the science that you do. If it's not aimed at the right questions, if it's going to have pivotal data that would change the course of our understanding, then you don't want to spend money on science that's going to lead to a rabbit hole. You want science that leads to the correct conclusion.
Well, there is a mechanism for getting there, and the National Academy of Science convenes every 10 years and does what's called the decadal survey. And this was the basis of Hubble being defined and developed. NASA always follows what the National Academy does, and this is based on hundreds or thousands of white papers contributed by the community, much debate, etc. So it's not pie in the sky. It's not the charismatic somebody or another says we must have a telescope that does this. It is almost a consensus of the community that this is what we need and this is what can be achieved. So there's the alignment. We have something called science traceability matrices. And this sounds all too NASA.
Oh yeah.
yeah. Diana, turn your back up. But what we try and do is to relate on a line-by-line basis the capability that science needs with the capability that we can implement. And there's a little bit of back and forth. No, we can't implement a 60-meter telescope in space yet. You can't have that, even if you want it. But we can do, if you allow us to fold it and do all the things we did with Webb, you could implement a 6.5-meter telescope. Well, the story goes on in that. So then we come to the next phase, which is use. And Diana is going to tell us a lot about that. Not only the beautiful pictures, but also the information we get. What are we learning about fundamental facts that pertain to what our universe is made of? And this is really important. And then after that, the next phase is we begin to consider the next telescope. So Diana and Woody and I are already thinking about the telescope that will be launched as a sequel to Webb, probably in 2050. And we have strong ideas about this. So So we can share that if you
Different
want.
ones too.
It takes
Well, let me,
25 years in the planning. Yeah, start now.
I'm writing down the date so we make sure we book you on time.
Yeah, that's right.
yeah, there's a schedule here. Okay, let me just kind of go to the next point of view. This was all been kind of NASA technical, but it's a sense of wonder, and I think that's important to remember, and that there is something underlying this that reaches me and reaches us all. And I think of what are the times when I've really had a great sense of wonder. Of course, being in a dark sky area and looking at the sky, yes. Have any of you seen a total eclipse of the sun? Does this not change your life in some way to see the totality? You see the sun as something live and visceral and wonderful. Paul and Laura have allowed me to talk, I think more than once, about the gnomon, where you can find out things about the sky just by making simple observations and watching the seasons change. Well, all these things are really wonderful. And one of the things I've done, and I've not shared here yet, but I love to get up in the morning and also in the evening and do time-lapse videos of the sunrise and the sunset and the dance between the sun and the clouds. And it's really sometimes, it's moving to me. Well, we have the same kind of thing happening. And Diana, if we could go to the infrared picture.
Yeah.
Okay, well, this is another sense of seeing the world in a different way. And I've just described some experiences that I've had. This is one I've not had, thank goodness, I would say. But on the left-hand side, you see an image of a firefighter entering a smoke-filled building. And there's a victim there, and the victim cannot be seen. And then the image on the right is with infrared glasses on, ones that have sensitivity to infrared and retransmit so that you can see things as they would appear in a different part of the spectrum. Well, guess what? Dust tends to scatter visible light, the blue and yellow light, etc., that we're used to looking at, and it makes it almost impossible to see through, as you see in the left. But when you get farther to the red, you do not have the same kind of scattering, and you also have thermal emission. So you see the body of the woman looking really hot, and also the firefighter. With infrared, we see the world differently, and infrared is really is really important, both from the point of view of Webb, of cutting through dust, and as Paul said earlier, it makes it a time machine. Before, when we talked, there was the popular description of James Webb Telescope as being the first telescope to see the first light of the first galaxies as the universe was formed. And to do this, you have to look, there's the phenomena of red shifting. All the objects and all the spectral lines that make up our world as we know it are shifted way into the red. And so if we want to look at the fundamental signatures of matter at great distance, we need to look in the red. So I guess I want to say one more thing, which is part of the wonder. What is the field of view of the telescope? A field of view, you know what that means from camera, where you have wide angle, narrow angle. Well, here we're talking about a very narrow angle. And you have to imagine if you held your hand at arm's length and you're holding a piece of sand in it. This is about the field of view that these marvelous images would have. And Diane, if you could do the next one, then we'll segue into Woody. And of course this is an image of the Eta Carini. So in this minute angle in the sky, all this is going on, and Webb is seeing this not only with the being able optically to do this. So it's the magic of optics, and this is something that Woody is the maestro of. It's the magic of optics. It's the magic of infrared. It's the magic of making stable structures and stable spacecraft and many things. But let's go and take a look at the optics that go to make this. So Woody, you're on, if it's okay with you.
Oh, okay, sure. Yeah, we'll just go from this right here instead of me showing mine. The James Webb is out at orbit around L2, the Earth Sun L2, which is about 1% of the. If you take the distance from the Earth to the Sun is 1 AU, it's about 1% beyond the Earth on the anti-sun side of the Earth, and so the sun is shining on one side of a big sunshade, and on the other side of it, it's cold, gets down to 40 Kelvin or 35 Kelvin, and the telescope is sitting there. You got to get the telescope cold in order to make these measurements. The infrared, you've got to suppress the background of the infrared by making it cold in order to make the measurements in the infrared. So that's what this does, and it looks out like that. Here's the basic telescope. You see the OTE, that'd be the optical telescope element, I presume, and the ISOM is the instrument module. All the instruments are on that side of the dashed line. The telescope is what's called a TMA, a three-mirror anastigmat, which basically says it's three mirrors plus a fine steering mirror, and the image quality is corrected well over the field of view. So you have a primary mirror, that's the 6.5 meter diameter mirror, and it's made up of segments, of hexagonal segments. We take a lesson from the local bee and wasp to learn how to do hexagonal, how to fill something up with hexagonal elements. It fills very nicely. Then there's the secondary mirror sitting out there. That images the field, that images the stars at what's called Cassegrain focus. And then there's a tertiary mirror that follows, that does two things. It images the primary mirror where that fine steering mirror is, and it images the stars back in the instrument module. A technical term is pupil. There's the fine steering mirror, the image of the primary mirror is called the exit pupil of the telescope. So you put the mirror there because then it is not affected by field of view. The beam is imaged there, so you put a mirror there, and you can point the creature.
Goodness. Wow.
So the various instruments then are on the instrument side. I dug out this June of 1997 document that starts out. It's summarizing a study that started in December of '96, and I worked with NASA on that and did a study. And in here they show one way to fold the mirrors, or the Goddard idea to fold the mirrors. In this case, some are up and some are down. Very complicated.
Can you show us? Yeah.
You know, here you can see. So some mirrors are up, and some mirrors go down.
Yeah.
What we did is well, this is hard to believe.
Okay.
When we were trying to come up with a better idea, we set up a table in the middle of our building and had scissors and paper and styrofoam, and we
Lots of high tech.
cut and played around with small models, and came up with what's called a table fold, and that's what you use. Basically, you have this mirror in the middle, and then the outer ones, they fold down, and that's what's used. And that's what I have a patent on with the other fellow who was working on this, a fellow who died several years ago named Wally Meyer. So it's a table fold. So that's what we did.
Oh my.
So let's go to the next chart then.
Woody, as we're doing that, I mean, you don't just go and look up a TMA formula and punch something in. There's a lot of work that goes into making something that's really going to work with all the parameters. Could you just say anything about what you did to approach this, to come up with something that was going to work so well optically?
Well, I know I needed a decent image over a fairly large field of view. Yeah, the 2.5 arc minute, the 5 arc minute field of view. In fact, go down a couple charts right
Yeah.
there. So the science module, the instruments have these mid-infrared IR or one called an imaging spectrometer, fine guidance sensors, and a near spec, and then the near cam. And most of the images we've seen, I think, have come from near cam. It's about 5 arc minutes across that near cam. So you have this fairly large. This is what is projected onto the sky. So the telescope needs to produce an image, a flat image, over a fairly large field of view, and it also needs that exit pupil. You've got to have that exit pupil so you can steer the beam and you can correct if there's line of sight jitter, you can correct that with a fine steering mirror, which you really need to put at an image of the primary mirror so that the tilt is independent of field. This type of requirement on the telescope cannot be met with a single mirror.
Mm-hmm.
You can't get the image quality. It cannot be met with what's used on Hubble, a 2-mirror Cassegrain telescope. You just cannot extend that field out that far. You could maybe do a Cassegrain with a corrector, but I didn't want to use any correctors. I wanted to use all mirrors. So the next step is to take 3 mirrors. It turns out with 3 mirrors, you can correct everything except distortion. You can correct everything. So that led me to a 3-mirror telescope. And to get a well-corrected over the field of view, you go to what's called an anastigmat. It's free of coma and free of astigmatism.
Woody, if I could just jump in for a minute.
Sure.
These squares that you see are the field of view of the individual instruments, but the telescope has to cover all these together. We don't switch from instrument to instrument. It has to be well corrected over this very, very large area. And the various cameras are filling part of this area, and there are reasons why it's only part of the area. But this is part of what made the optical design work very difficult. It would be a very different telescope if you had to switch filters between instruments or have instrument changers.
Right. That was a trade. You could trade between sharing the focal plane or sharing the pupil. And if you share the pupil, you're giving up energy. So we didn't want to do that. So we wanted to share the focal plane. So we image these fields and then have individual instruments looking at each of these fields.
So the 3 mirrors was your innovation, Woody. This was your eureka moment.
Well, it's classical design. It's a fellow named Dietrich Korsch wrote a book on this. And I use his work. It's very classical. In fact, everything I did was based upon what other people had done before me. Every single thing.
Well, let me say that Woody was the one who could implement this, and there were many optical designers all around the world working on it. But Woody came up with the right answer.
I taught Goddard how to design a 3-mirror anastigmat.
Wow.
Okay, so we'll go up a chart or two. Let's see where we're at now. That's the field of view of the near cam. It's 5 arc minutes across there. We don't need to talk any more about that.
Okay.
Well, I do want to point out the coronagraph masks.
Okay.
And Woody, can you just say a little bit about? Can you explain very briefly what a coronagraph is? Because this is going to come up later in what I'm going to talk about.
Okay, in a coronagraph, the term comes from the sun. To study the corona of the sun. And back with Skylab, we had an instrument that I designed that takes pictures of the corona of our sun. It blocks what it does. It blocks the direct radiation from the sun, and then suppresses stray light around it, so that you can then see this the corona. So we take that term and apply it to stars. So in this case, what you want to do is to block the bright light directly from the star, and then re-image to a pupil. Another, you re-image the telescope primary mirror back to another pupil, where you would put in what's called a chronograph mask, which basically blocks radiation from the edge of the primary mirror and would block radiation from the spider, the structure that holds the secondary mirror. And there are other tricks that are applied also. I'm not sure all the details they have in their particular design, but the basic chronograph would put a finger over the image of the star and block the scattered light from elsewhere by having a pupil mask, a mask at the pupil, the image of them.
Woody, maybe you would comment, or Diana would comment, that this is not just masking, but there's all sorts of stray light paths that can come into a telescope. But the contrast ratio, you have to knock down that center star to do what you want to do. For what Diana's talking about, by a factor of how many million?
A lot. 10
Yeah.
10 to the power of 16, 20, something like that.
10 to the 20th?
No.
Well, so for James Webb, it's a little bit less than that.
All right, so we're talking over 1 billion to 1. It's like blocking a lighthouse so you can see a firefly next to it.
Okay. Yeah.
Yeah, and I'm not sure
yeah,
I'm not sure what James Webb is doing for the missions that are directly looking for Earth-like planets around other stars. They want to knock it down by a tenth of a billion. Okay, I have up there, and Diane's going to use some of this, but I also calculated what the size of that 2.2 augmented field of view is, and it relative to the size of our sun, it's about 6%. It's about, so if you look at that full moon, that nearly full moon,
Yeah.
it's about 1/6 of that, and if out at 1 mile, it's a little over 3 feet. So, and I'll do some speculation.
This was a lot of calculations, but you really couldn't test it until it went out and deployed. Wow.
Everything is math. Everything is math. We do it all with mathematics, and math works.
And Laura, very extensive tests were done on this. That's part of what cost so much and took so long. That tests were made. If there were any surprises, modifications were made, that kind of thing.
Well, I want to just mention from the chat room, Gopal Vasudevan is saying the coronagraph design was performed by my colleagues, Dr. Steve Sommerstein, Dr. Volker Tolles, Dr. Rick Lyon, and himself, fabricated by JPL later. So, wow, so many hands on all of this.
Yeah, thank you, Gopal. I didn't know you'd be on. We would have invited you to be part of this.
Yeah. Well, we'll talk to you in just a bit. Yeah.
There's a number that you learn in chemistry, or Avogadro's number, 610 to the 23rd. It's a big number, That's a lot of zeros. And it turns out to be the number of atoms for carbon in 12 grams of carbon. So carbon 12. So the 12 grams, you end up with that, and it applies to any element. It's called a mole. A mole is, in this case, is 12 grams of carbon, which is not a lot. Mm-hmm. It just happens that from the Hubble Deep Field, there's an estimate of 10 to the 12th galaxies in the universe. 100 years ago, we thought it was 1, so it's about 10 to the 12th. And I've heard estimates there's about 10 to the 12th stars per galaxy. So there is roughly Avogadro's number of stars. Now, I don't know what that means, but you could imagine that the universe is one mole. So 1 mole of stars. Anyway, that is a totally non-scientific
Mm.
speculation.
A somewhat unfortunate name because many of us have different connotations with
To
moles.
moles, yeah.
Yeah.
But nevertheless,
I wonder if Gopal would comment a little bit more about the chronograph that is on James Webb.
Oh, Gopal, would you like to let's get him on?
Okay, so back when we had originally starting off on the NIRCam instrument design, there was a little bit of an interest and push from a fair number of people who have been working on coronagraphs on various things. There was a project that was also going somewhat concurrently as a design thing called the Terrestrial Planet Finder, and which never came to pass. And Tony can tell you a lot more about the Terrestrial Planet Finder than any one of us could. But in any event, some of us had been working on different types of chronograph designs, and we made a pitch to Professor Marsha Ricci at University of Arizona, who was a PI associated with NIRCam, that, hey, could we please put in a chronograph mask in it? And we were told, sure, as long as you can do the entire design and it's not going to cost the project much. So we took it upon ourselves. We found internal R&D funding, found this thing, and Steve Summerstein said, hey, I know how to do this, how to make these masks. We will use it how the inkjet printer works. So we will make the masks by dithering the dots and putting it on there so that the effective mask, the attenuation, or how much the light gets dimmed at each part, is based on how much of the light goes, how many of those dots overlay on top of each other. So we did some simulations, and we got a lot of help from from Dr. Rick Lyon, who is unfortunately not with us anymore. He was at Goddard, and he looked at the design and he said, yep, it does work. And then we fabricated some of these and gave it to Volker Tolles at SAO, who tested it in his lab and said, yep, it does work.
Yeah.
And then we got all excited. I mean, I must confess, what I'm talking about didn't all happen in 1 year. It happened over multiple years, unfortunately. And then we finally came up with the specs and everything else. And then Marsha decided that it was better for JPL to fabricate it. And they did. And came out, and I'm so glad it was finally included in the NIRCam overall, because we have got some really good exoplanet pictures recently.
Mm.
Yeah, I'm going to show some of those.
Gopal, thank you very much. That's a great segue to what Diana is going to talk about. Woody, I think we're going to move on to Diana, if that's okay.
Wonderful, wonderful.
Yeah, well, thank
you,
you,
Woody.
Woody. Thank you, Gopal.
Thank you and thank you, Gopal. Good to meet you.
Well, this is it, of course. This is a model in a way that we can't quite see, of course. But the real thing is to see the images. And I just wanted you to see this for a second to jump right into what Diana has prepared for us.
Yeah, just a little reminder of what we're actually talking about right after so many diagrams. I mean, this is not to say that this should be simplified. As we saw from Woody, there's so much work that went into it, and way beyond my expertise. But taking a big step back, this is what's out in space. Of course, with those Mylar shields deployed. Well, basically kind of the way you're seeing it here, except it's in space and not reflecting a building like in this picture.
But fascinating to know what goes on. Yeah.
So I just wanted to jump right into some pictures. The first one is one that you've seen before, and it's not from Webb. Just find my cursor here. There we go. And one small adjustment to my title, I guess. So I'm a professor of physics and astronomy. which means I'm not a professor of astrobiology. However, it all comes from the cosmos, right? So astrobiology is life in the universe, but I would say that to understand that it's impossible to separate from understanding our cosmos, our galaxy, our star, our planet, and of course all of their siblings. So this is a picture that you may or may not have seen before. It's kind of supposed to show both time and space, how the universe started from nothing because we don't know any better, and expanded at the beginning very quickly, and then later on a little slower, and now of course it's expanding very fast again. But I won't get into that. And I promised, well, we promised last time that one of the areas that Webb is looking at is looking back in time and far in space, which, as Laura said earlier, it's essentially the same thing, right? So you when you look very far into the universe, you're also looking very far back in time. All right, so if everyone's ready, you have to be really mentally ready for this, okay? Because otherwise I can't move on. All right, so let's start with coincidentally, also one of the first images from Webb. So this is an image that contains a lot among some things. So that maybe the thing that jumps out first are those points of light with the diffraction spikes on them, right? So the kind of 8-pointed star. Those are actually stars, and they are stars in our own Milky Way galaxy, not outside of it. But just about everything else that does not have those diffraction spikes are galaxies. And so I don't know, Laura and Paul, can I get our audience to participate a little bit? Is it okay?
Oh, yes, please. Yeah.
Unmute to answer questions. I think it's a way to remember things better if people can kind of think of the answers on their own without me giving them all the time. Okay. So I guess I just want to take a quick poll of what people see in this image, right? So I told you about the stars and the galaxies. But if you look a little closer, something, I don't know if you guys, can you see my cursor on?
Yes.
Oh, yeah.
Okay, good. So something like this. This is a galaxy. This is a galaxy. This is a galaxy, kind of like the Milky Way, a spiral arm galaxy. What is this?
Oh, this, yeah.
What is that?
Ellipsoid thing.
She wants you to guess.
Oh, we're guessing.
Yeah,
Yes.
yeah.
This is a quiz.
It's Sunday morning.
Two galaxies being stretched by a black hole, or two galaxies kind of colliding and merging. I don't know.
Or the movement.
Yeah, so I like your first idea there, Laura. So it's a galaxy, the light from a galaxy that's being stretched by something massive, not a black hole in this case, but dark matter. So there's dark matter that, as the name says, is dark, so we can't see it. We don't receive any light from it. This is why it's so difficult to study even with Webb, because we don't get any light from dark matter. But we can see its presence from its mass. And the mass of any object, but particularly very massive ones, so big clump of dark matter, is able to do something very similar to what an optical lens can do, which is distort light. So we've got dark matter in the foreground that, again, we cannot see, but we know it's there because its mass is distorting the light from, for example, this galaxy. And this galaxy is in the background of the dark matter. Dark matters, I want to say it's in our galaxy. I'm not going to promise it's in our galaxy, but generally, in an effect like
safe conclusion.
Yeah, it's dark matter in our galaxy, and it basically just kind of bends the light of anything that's immediately behind it. So you get an effect like this, and then here's another image right here, and then you've got these lines here too, and you can kind of see more of them as you start looking for them, right? All of these distorted galaxies as a result of dark matter's mass in the foreground bending the light.
So isn't that one of the mysteries of the universe, that it starts out very uniform according to looking back in time, but now it's all clumped? And so what are the forces that are causing it to get lumpy?
Right. So dark matter, just like galaxies, sort of organized into clumps after initially starting in a soup of atoms, soup of particles, really subatomic. So pieces of atoms, which eventually, as the temperature cooled down after the Big Bang, they were able to assemble into larger and larger structures. So when temperatures are very high, even atoms cannot hold together. So protons and electrons will separate. As you cool down a little bit, I'm not going to give you exact numbers because you won't need very much, but as you cool down a little bit, you end up with atoms. So now, so when you raise the temperature, things move faster. And this is why when you have very high temperatures, the motion of electrons and protons is such that they just can't settle down to assemble into an atom. So when you cool down a little bit, then you can get atoms. And when you cool down even more, you can get molecules, which are combinations of atoms, because now things are moving even slower, and they can kind of settle down into a bigger structure, right?
Yeah, and they like to fit together and attract one another and coagulate.
Yeah, but you need to calm down the temperature.
They like to form cliques.
Yeah, exactly. All right, so I'm gonna move on to another image, but I do want to say one more thing about the sun, which is that some of the galaxies we see in this image are from 300. They formed 300 million years after the Big Bang. So I think this is, can I do percentages in my head very fast? 300 out of 14 billion. Let's just say it's about 1% of the lifetime of after the beginning of the universe relative to today.
And so this does tell us something that we didn't know about dark matter, because now we're seeing where it is and how it's behaving and what it's doing. So is this
That's a good question. Yeah. So Hubble saw images like this too with distorted light. But yes, images like this do tell us a little bit about where it's localized and exactly how it's distributed, and a little bit about the mass of that particular clump. I think Woody has a question or a comment. Go ahead.
I was just going to comment on the brighter objects, the brighter point sources. You see 6 lines or 3 lines. They're at 60 degrees. Those are because the mirrors in the telescope are hexagonal. So that's generated by the telescope, not by the star itself.
Yeah, I was hoping you'd say that.
Also, Jean is asking, why is the universe in a tube? That previous illustration, that's just a slice that you're able to see, and
so that's
from early to present time in that. You might want to
it's difficult because how do you portray that as the universe goes from nothing or a point to what it is today, which is very large, but also no edges, right?
Yeah.
And also show that expansion happened over time. So this is kind of the best we can do in 2 dimensions. So it's a very, even though it's a picture, it's a very schematic way of showing all of that.
And see the timeline, 13.7 billion years. So you're showing this. And
there's no edge and there's no tube. This is just a very poor way of showing the time dimension, the 3 dimensions we can see, and also but we can't on top of that show you how the universe doesn't actually have any edges. I can't put that on the slide.
So we have 3 dimensions plus time compressed into 2 dimensions. So it's not a realistic view of the universe in that sense. But it does tell us something about the rapid inflation at the beginning of the universe and the accelerations that we're seeing now, which are due to dark energy.
Yeah, that's right. So I would say this is more, if anything, this schematic shows the change over time.
Okay.
Try not to imagine that the universe actually, that the space part of it looks like this.
Got it. Thank you for that.
But it's very difficult. I can't visualize the universe. I don't think anyone can really. So like Woody said earlier, we know this from math and measurements. So we can put it down in math, but no one can really imagine what it's like because we can't think in so many dimensions and imagine something
beyond the limits of our imagination. Really.
Basically. Thank you, Laura. Yes. All right, so I've bored you enough with this picture. But the point is that we're seeing a lot in this image. We're seeing some of the instrument characteristics, like the telescope's characteristics. We're seeing real science. We're seeing a lot of galaxies from very early in the universe. And the light we're seeing from those galaxies was emitted by those galaxies 300 million years after the Big Bang. That, you know, that very, very early on. And it's only today getting to us. And thankfully, we have something to collect it with now, which is the web.
That's
All right, so
the challenging part about this is just understanding that concept of time. I think for me, just that we're looking at something like you just mentioned. We're looking
Really
back in
seeing
time.
in 4 dimensions.
Yeah,
aren't we?
exactly. Exactly. I just mentioned, Anne asked the question, exactly how do we know what are the galaxies? What are the stars? How is that? You know, she said she wanted to know more about how we can determine what is what.
Just a quick answer.
A quick answer.
yeah, I would say the quick answer is the distance. So I'm not going to get into how we measure the distances. But based on distances, we can say when something, and of course, a little bit what they look like, but sometimes it's hard to tell. Based on distances and a little bit on what they look like, we know whether it's something inside our galaxy or something outside of our galaxy.
Perfect.
And what are we seeing here with Stephan's quintet?
Yeah, so Stephan's quintet is a group of galaxies. This is definitely outside my area of expertise, but as an astronomer, I should know a little bit about it. So a quintet is a group of 5, right?
Yeah.
So here's a question for the audience. It's kind of straightforward to see 4 galaxies in this image. Maybe I shouldn't say straightforward. Maybe not everyone can find them, but where's that 5th galaxy? The leftmost galaxy here, this one, is actually very far in the foreground relative to the other 4. Okay, so it's not really associated with them. If you think about the distance, one of them is very, much closer to the Milky Way than the other 4. And then what's going on here?
There's 2 centers, so that would count.
2 centers. Those are 2 galaxies, that at some point have collided, and well, I don't know today where they're at, but eventually they might merge into a single one. But currently, you can still see the leftovers of the 2 galaxies that.
Rather like the Milky Way and Andromeda, right? They're merging.
Down the road. Yeah, the same thing might happen to us many billions of years down the road.
Yeah.
Okay, so I'm gonna get a little technical here, but I want to show you that same image and split first of all from 2 different instruments, right? So one of the instruments is the NIRCam instrument, and I think that's on the left. And then the one on the right is the MIRI instrument. And the main difference is that MIRI can see at longer infrared wavelengths. So even redder light than the NIRCam. Sorry, it's NIRSPEC on the left. My bad. So this is NIRSPEC here. But again, so we're looking at sort of shorter wavelengths, and you can see here, it's very small, 0.6 micron, that's roughly in the visible light regime, and then 1.6, 1.8, and 4.7 are definitely in the infrared light wavelengths that we cannot see with our naked eye. And so this is showing the different types of atoms or molecules that we can see when we look at these different wavelengths. It's kind of one way of showing why we need to observe at these very long infrared wavelengths. So here is a picture of the same one galaxy, the one at the top here. And by the way, this galaxy, a lot of these galaxies, they're bright in the center because they have a giant, very massive black hole that's just eating stars nonstop and emitting light as it does so. It's really not light from the black hole that we're seeing. It's light from the disk immediately surrounding that black hole through which the stars are being funneled in. So it's kind of like the last light from the stars in a way before they get absorbed into the black hole. Devoured. Thank you, Tony. Yeah. So here we see these images at different wavelengths, and they're showing us different atoms or molecules, even though it's an image of the same part of the galaxy. So if you look at in one color, you can see emission from hydrogen, then you can see emission from iron here. Here hydrogen again, and then here molecular hydrogen, which is 2 hydrogen atoms that got together to make what we call H2, which is actually a molecule because it's more than one atom. And then on the right, it's a little more complex, but not too bad. We're basically seeing the motion. So we're seeing argon atoms or ions here, neon ions, and molecular hydrogen again. But we're also able to see the color coding tells us the motion relative to us of these atoms. So anything that's a little more yellow is gas that's moving away from us. And anything that's blue in those images is gas that's moving towards us. So it's still in the same galaxy, but within that galaxy, there's a lot of turbulent motion. And you can see it from the color coding here. All right, any questions? I see a lot of comments in the chat, so maybe this is a good time to take some questions on this.
Well, Michael's asking the question, previous guest a couple of weeks ago. We're looking back. I'm also curious to learn what matter is older and in front of our position in the expansion. Are we on the leading edge of this expansion, or nothing in front of us?
This is going back to that idea of there is no edge to the universe, nor surface, right? A lot of times,
Younger, older.
Yeah.
It's just the we're just light from further away, but it doesn't make it older than us.
Yeah, I think the best way you can think about it is a balloon that's inflating, and if you draw a picture on the balloon, as the balloon is inflating, that picture stretches also, right? Now we are not quite at the point where galaxies are stretched to the point of being torn apart, but space is stretched that way. And then you don't have the balloon surface. So there is, it's not really meaningful to talk about leading edges or trailing edges because there are no edges.
Gotcha.
But I don't expect you to visualize that. It's just your question cannot be answered, which is a good thing, I think.
And
right?
Reed is also asking the question, will the black hole at the center of the galaxy eventually devour the whole galaxy?
That's a good question. Eventually, I think this is probably a whole lifetime of the universe over again down the road, if not longer.
So if all the black holes devour everything, eventually maybe there'll be the next Big Bang. Maybe it'll just throw it all up again. I don't know.
Yeah, eventually. But I think it's just the reason I'm having a hard time answering that one is because, or hesitating, is because the time frame for it is so long. I think it's actually beyond the current age of the universe. Like it's probably orders of magnitude, so tens of times longer than the current age of the universe. So far in the future that it's
a big unknown.
Yeah.
But no data yet on that one.
That's right.
Yeah. So when we reincarnate way in the future, we'll know, I guess.
That's what it's going to take.
Yeah.
But I don't see any reason why it would eventually. All right. So here's another galaxy, and I promise I'm gonna move smaller and smaller as we go on. So this is called the Cartwheel Galaxy. It's formed from a collision between this galaxy and probably a smaller galaxy about 400 million years ago. So that's close to half, let's say 500 million years ago, and the universe is 14 billion years old. So maybe that's closer to a few percent. Yeah. So this is so the spokes that we see here, right? We're still seeing the leftovers of the turbulence of that collision. And as this galaxy and the one it collided with are evolving, they will eventually settle into something that's a little different from either one, but that's going to happen far into the future. But today what we can do is with Webb, we can see the spokes. It's okay. We can see the spokes of the cartwheel a little bit better. And we can see individual stars, these blue massive stars. And of course, two galaxies, satellite galaxies, probably to this one nearby. But we can see stars within this galaxy. And in particular, we see these, it's a little hard to tell, but some of them, so the blue dots are young, very massive, very luminous stars. And then the red ones are a different population. They're cooler stars as well. And you can see the color used to make this image visible in the visible, so we can look at it, was set up that way, so we can see two different populations of stars in there.
It's interesting to see the spiral galaxies. They're just two arms, right, spinning. It's just
it's actually multiple arms, but in here it's true that you have, it's basically like a distorted spiral galaxy. And normally you wouldn't have a circumference that connects the arms like this, but that's as a result of the collision. So it's almost like it's a mix of, oh, I see you're looking at this one. Yeah, here it does look like it's only two arms. It's true. Yeah, our Milky Way has a number of arms, not tens of them, but several arms. But sometimes a couple will be prominent. Yeah. And then here you see that you don't have the arms connecting all the way around, but here there's more of a connection, and that's a result of the collision. All right, so moving into our own galaxy now, I'm going to show you a very ugly picture. So I actually showed this in my class this week, and it took me a while to find this picture, but I think it's important because it really showcases what I'm about to show you next, and really the infrared capacity or capabilities of Webb. So this is this big picture is in the background, an image of the Tarantula Nebula. So it's a big clump of gas and a little bit of dust, but mainly gas, that is in our galaxy. And it's a place where stars are being born as we speak. So it's called the star formation region. And what I'm highlighting here is a small part of the Tarantula Nebula, and this is seen at visible or optical light wavelengths, right? So what we can see with our own eyes. So one thing to really notice is just how cloudy it is and how sort of ghostly, and you can see stars through some of this gas, but not all that much. And in particular up here, there's a bit of an opening that we can see, but the gas is just scattering all the visible light away, so we can't really see through it. But then you take this to the infrared wavelengths, and so the same picture I just showed you is just a little bit rotated. Here's that little clump, that little opening that you could just barely see in the previous picture, and you can see it really well now at these shorter IR wavelengths, and of course also at longer IR wavelengths, because now the light that we're capturing, the infrared light, is light that does not get diverted by the gas. So it can go straight from the stars in the background. Right.
Wow.
While shorter wavelengths light just kind of gets diverted. And the net result is similar to why the sky is blue. It's kind of blocking out. We lose light from, we don't get the from those stars arriving to us because the gas is just scattering it all away. So there are a few things here. I'm not gonna, I made my class sit down and think about this for about 10 minutes until they found everything that that you could learn from these two images side by side. So these are both from James Webb. One thing I am going to note is that maybe you'll wonder why, when you look at even longer wavelengths, how come you don't see even more stars, right? I thought we were supposed to see through the dust and the gas along wavelengths. So we see lots of stars down here, but here they kind of gone. So what it is that the stars here are massive blue, mainly blue stars. So all it is that the stars themselves emit most of their light at shorter wavelengths. So you can still see them at shorter infrared wavelengths, but over here, longer infrared wavelengths, they just don't emit that much light. So it's a bit of a different
You have to be tuned to pick up the light that they are emitting in order to see them then?
Yes, but they themselves are not emitting that much light anymore at such long wavelengths.
Okay.
So we just don't see them. We see
why
through
is
the
that?
dust, everything is fine. Infrared light is doing what it's supposed to do. It's just that the stars are so much fainter at those very long infrared wavelengths that we don't see them anymore.
So
But
this
we
is
do,
the difference between
yeah.
blue and red stars then? So
Yeah. So in a way, this red star here, it is also fainter in this image, but it's relatively brighter. So in a way, we still see it here because it does emit more light at longer wavelengths, even though most of its light is still over here. But it doesn't completely disappear like many of those stars because it's a little redder. So we're still getting a little bit of red light even at even redder wavelengths, if that makes sense. But what we are seeing here, so in blue, we're seeing some of the hotter dust. It's not all that hot, actually. And then in red, we're seeing some of the cooler dust. So we can actually see things that are a little cooler at longer wavelengths. And it's a little hard to see, but this point here and this point here, those are stars that are called protostars. So they're just about to start burning hydrogen. They've collapsed. They've started forming from the hydrogen cloud that initially was there, and they're just super young, very young stars. And they're we can see a little bit of a bubble around some of them, and that is the dust and gas that they've blown away as they started getting hotter. So these are things that don't appear as clearly in this image, but as we go to longer wavelengths, we can see what's happening in the same region, right? But we see events and objects that we cannot spot as easily at other wavelengths.
So nice to have all those different layers to...
Exactly. That's why we care so much about the different layers of IR, infrared light.
So it's not just pretty pictures. There's a lot of information about what's really happening in these regions.
Yeah, and of course, there's a lot more than what's in these pictures, but I don't even know enough about it. But you can already start seeing a little bit of that just in the layers. So this is an image taken using one of the, oh my goodness, one of those coronagraphs that I made Gopal and Woody talk about earlier. Because here's where we use those coronagraphs. We use them to block out the light from this very bright star, so that we can see the planet next to it. So this is an image of an exoplanet around a star much bigger and more massive than our sun. It's called an A-type star. And the little star symbol is meant to show where the star is located. But we can't give you an image of the star with the planet because you won't see the planet.
Give us a symbol of its location.
Yeah, it would just cover this entire square. It would just be light from the star. But just to give you the location, we block out the star, but the location of the star is here. And of course, it is much brighter than a planet. But once you block it out, you can zoom in and see the planet itself. Now, and this is also seen at different wavelengths, here with NearCam and here with MIRI, longer wavelengths on the right, showcased by the redder colors, and shorter wavelengths on the left. One quick note is that these weird bars around the planet, those aren't aliens or additional planets. They are just artifacts of the way that the optics are set up for that particular instrument. And they're not a problem. They're not unexpected. They are not keeping us from learning about the planet. Ultimately, what we really want is a spectrum of this planet. And we're starting to see that here at the 4 images. So this is a planet that was discovered in 2017. It's not discovered by Webb, but we're seeing it in a lot more detail. And we're seeing all these wavelengths that we would not be able to see with any other telescopes. So that tells us about the composition of the atmosphere of this planet, which, by the way, is a gas giant like Jupiter. So it's not an Earth-like planet, but we got to start somewhere, right? Yeah. Okay. And I think I'm basically on my last set of slides, but don't worry, it's not very long. Actually, so one thing I wanted to show here is a circle is where the orbit of Neptune, right, which is the most distant planet in our solar system, would be relative to that star. So this planet is 2 or 3 times
Even
further out from its own star than Neptune is from the sun.
I see.
Do we
and
know the
still
temperature of the
emitting
star?
light. Yeah.
A stars are very hot.
It's an
Do I know
A
it by heart?
No, it's an A star.
It's an A star, that's
okay,
right.
thank
Oh,
you.
actually, I do know the temperature. It's about 10,000 Kelvin. So how many Fahrenheit is that?
Well, we'll do Kelvin.
We'll do Kelvin. I know that because that's where, anyway, there's a reason. But normally I don't remember these things. You got lucky. Okay.
So they don't understand where some of the light or energy from some of our big planets come from, right? And so is that true of this? I mean, that's a long ways from a star.
Wow, Laura, you got it. Yeah. So yes, Jupiter and Saturn are emitting more light in a way than we would expect if they were just taking in light from the sun and sending it back out. Which is fine, right? That's what the Earth is doing. It's taking in light from the sun. We're keeping a little bit, but not that much. And then it's kind of re-radiating it back out because the Earth itself is not making any of its own light. It all comes from the sun. Jupiter and Saturn are doing the same thing, but they're emitting a little more than they receive from the sun. And the reason for that is that they're still, when planets first form, they're very hot, almost as hot as a small star. And then over time, they cool down. Jupiter and Saturn are still cooling down. So some of that heat that that came from them forming is still in there. It's a small fraction of the overall light they produce or heat they produce, but a little bit of it is still there. And what we're looking at here is a very young star. So this star is pretty hot compared to Jupiter, compared to Saturn.
But also
it is the temperature of a small star because it's just forming. And everything is still kind of molten and high temperature.
So what do you think the temperature is?
Of this planet, I should know, but I don't know because it's not my planet. I want to say probably like 2,000 Kelvin, something like that. That's what I was thinking. Yeah. So 4,000 Fahrenheit.
Yeah, about 4,000 Fahrenheit.
Pretty hot.
A hot place. Yes.
You don't want to be there. Yeah, but in something like a billion years, it would probably be as cool. Well, actually, a lot cooler than Jupiter and Saturn because it's so much further away from its own star. Although its star, it's more massive. That said, in a billion years, the star itself may no longer be around. So that's a whole other issue that you can. But I don't want to get sidetracked. The opposite of the planet, right? All right. So here is a little reminder of how we detect planets. Of course, we detect planets in the way I just showed you. We take a picture of it, but that is very rare. We can only do that for very nearby stars. As soon as you get a little further from the solar system, you can't really see planets anymore. And you can only do it for very young planets. And they don't stay young for very long, just like kids. So the vast majority of exoplanets we know about, we find in this way by observing how they pass in front of their stars and cause a little bit of a dimming as a result of the shadow that they cast onto the star. And the dimming is going to be different at different wavelengths. And that tells us about what the atmosphere of the planet is made of. So here is a finally actual example from James Webb. And so remember that the dimming we just saw, here are points of data from observations with James Webb. And we can see the dimming of this hot Jupiter called WASP 39b. I need to remember that at different wavelengths. In this case, the blue points, which I guess don't show up very well here, but you can see it in the zoomed light curve. So the blue points are observed at, even I have to squint, 3 microns, and then the green points are longer wavelengths a little bit, 4.3 microns, and then the red points are at even longer wavelengths, 4.7 micron. And the difference, you can actually see that they're not all overlapping. I'm sorry, Woody. They're not all overlapping. So the green points are kind of the deepest part of the transit, and then the red points are a little shallower. They're overall a little bit higher, and then the blue points are in between.
Mm-hmm.
So what we can do is take the depth of this bucket, of this transit, at different wavelengths.
Okay.
Not just those three, but even more, split it into even more wavelengths. And plot the size of that bucket over as a function of wavelengths, and then we get this, which is how deep the transit is on this axis as a function of wavelengths. And lo and behold, at around 4.2, 4.3 micron, at that specific filter or wavelength of light, the transit is a lot deeper than at the other wavelengths. And that tells us that something in the atmosphere of the planet is absorbing light more than normal, light from the star,
Okay.
at that wavelength. And what that something is carbon dioxide for this planet. So I should say that this is a Nature paper that I actually could have been a co-author on, but didn't really do anything. So I opted out. So a paper that was published in the journal Nature, and it is the first clear detection, and shall I say really clear, if you see this bump is really obvious here. Did really well, of carbon dioxide in the atmosphere of an exoplanet.
Okay.
Is that surprising?
We're going to ask, so are there natural means of creating carbon dioxide? What does it mean? Does it mean that there's life? Does it mean there's an atmosphere? What does it mean? What are the implications?
Yeah, so I would say the implications here are we're expecting carbon dioxide in a planet like this.
Because it's a gas giant, right? So
it's a gas giant, that's right. But we haven't been able to detect it this securely, this clearly ever before in a planet outside the solar system. So it is a little bit of a baby step in that sense, but the size of this bump tells us about how much carbon dioxide there is in the atmosphere of this gas giant. And it also, that tells us about the other types of molecules and atoms that you can have and where in the atmosphere they can be in order to explain or allow for the carbon dioxide in this amount to exist. So we can learn a lot of indirect things about the rest of the chemistry because of this detection.
And relatively speaking, is that a lot? Is that a big bump? Meaning relative to the overall atmosphere?
It's a lot, but it's a lot. It's enough to be detectable. But I should say that most of the atmosphere of this planet is still made of hydrogen and helium. All gas giants are primarily made of hydrogen and helium. Unfortunately, hydrogen and helium are gases that don't really absorb light at too many wavelengths. Helium in particular just doesn't really interact with light very much. It's not dark matter, but it's just an atom that doesn't interact with light very much. And so when we are looking, so we know that hydrogen and helium are there, and we know that because otherwise the planet wouldn't have the density it has. So it's a very different argument. It's a very low density planet. So it cannot be made of anything heavier than hydrogen and helium primarily. But since we can't detect those very often, we use the other molecules to study the chemistry of the planet's atmosphere. So carbon dioxide is not that abundant relative to the hydrogen and helium, but it is there.
So carbon dioxide is interesting with life if you have some free oxygen, right? So it doesn't really tell us anything about could life be there. It just means, this can exist. Have you, what other data on exoplanets have come in yet, or is it still early in the game?
Yeah, this is early in the game. This is the, I would say, the main result so far. It's only been 2 months since we started getting science data.
Right. How do they prioritize what the web is going to pick up? I mean, who gets to set the agenda of where we're looking, what we're looking for, and let's do the scan of the universe? Who is setting the menu for what you're going to look at and when?
So part of it is right. So the Space Telescope Institute is setting the menu, and they're just trying to fit in everything. Webb can see a lot of the sky at any given time, but there are still some parts it cannot see during some times of the year. So that contributes a little bit to the scheduling, what is observable by Webb at that particular time of the year. So maybe you can look at a certain galaxy, but you can't point to this planet because it's behind the sun, or there are other constraints. But beyond that, it's really, I don't really know what goes into the schedule. Maybe, so as long as they execute all of the observations that were successfully approved in the first year, and as long as they get executed sometime in the first year, I would say astronomers are pretty happy. Just give me my data.
Are they going to do a kind of a 360 and maybe do that in the spherical sense? Or do they have a main mission? Are they going to look for, these are the most promising exoplanets we detected with the Hubble and other telescopes, so let's go take a second look? Or what is the agenda? What are they?
It is all based on what astronomers so astronomers will write an application and they say, I want to observe this for this long. And then the best argued applications are selected. So it is not NASA, it is not Space Telescope that makes that chooses the science. It is astronomers that all have to argue for their particular planet or galaxy. And that's ultimately how it gets decided. There are some exceptions for the teams that made the specific instruments. But even then, it is through selection, a very selective and competitive process that they selected the science that they want to do. So NASA doesn't make that decision uniformly. It's really the astronomers.
Gotcha. Do you have any other images to show us?
I have one more, if folks want to see it. I didn't want to overstay my welcome, but I just wanted to show this picture of.
Oh yeah, we heard Jupiter was.
Yeah. And then I'm just gonna make sure people are awake and listening. I'm gonna end with some questions here. So you're gonna tell me what we're looking at in this image. So let's start from the outside in. So I tried to make this image a little bit brighter, but ultimately, it's supposed to be relative brightness. So I'm not gonna exaggerate anything. But we see a little object here. But we also see kind of a ray of light that comes from the edge of the image, and it's kind of brighter towards the left, but we don't really know where it comes from, at least not by looking at this image.
Why don't you just tell us?
So these are diffraction spikes, diffraction pattern. In this case, it's from the actual aurora of Jupiter, and this is the end of a diffraction spike from one of Jupiter's brighter moons called Io, which is much further out from Jupiter. And so we don't see it in this image, but it does orbit around Jupiter just like the moon orbits the Earth.
And it would have that focused light. A little moon would have then a beam as opposed to just more.
Yeah, it would cause these diffraction spikes because it's very bright. It's in our solar system, so as a result, it's very bright, and it's bright because Webb can pick up light like that. It's amazing. This is why it's so big.
The other dots and what about the split beam?
What is this? Yeah, what's that? Oh, you want me to tell you?
Yeah, just tell us. These other moons?
We give up.
That's a moon. That's another moon. Yeah, it's on Jupiter. It's a much smaller moon. And then we can see there's a little ring here that you can just barely make out. Jupiter has rings. Did you know that? There you go. And then in here, there's a tiny, tiny point. It's another moon of Jupiter. And the rings of Jupiter are actually made from material that is evaporating or just coming off of these two moons here. So I think this is, one of them is Amalthea. The other one is Adrastea. I want to say that this is Amalthea and this is Adrastea, but I might have them flipped. And these moons, material coming off of these moons are making the rings of Jupiter.
And then you see the great red spot.
That's right, the red spot. And then it's kind of highlighted by the phenomena we're looking at. So the lightning and aurora of Jupiter are kind of shown in blue. And then we have a fair bit of some of the higher clouds in the atmosphere of Jupiter are shown here as well. And then I'm just going to move to this one, and I promise this is the last one, which is a different color coding scheme. But I'm going to have to read off for this one because I don't remember. But the redder colors are showing some of the hazes in the atmosphere of Jupiter. And then the yellows and greens in here are showing hazes around the north and south poles. And finally, the blues, which aren't as obvious, but everything you kind of see in blue is light from clouds that are a little deeper in the atmosphere of Jupiter. We might think that everything we see, all the clouds in Jupiter, all those bands are all of the same height. That's not the case. But we can't show that in 3D. And so we use color to show the different bands.
And Woody says, why white, not a red spot?
It's the filter.
I think that's supposed to be part of that yellow and blue. So the bluer area in this spot is supposed to come from further, so deeper into Jupiter. So they just color coded more by phenomena and
filters
and depth in this case than by what you're used to seeing in the visible.
I have to say how
This is a
fond
mixed image, right? The layered image that's adjusted by I guess astronomers to show us different parts.
I have to say how fond the universe is of vortexes and spirals, right?
Yeah.
It's interesting.
That's a good point. Yeah, it looks like a little galaxy in there. But...
Yeah.
Well, everything's revolving around everything else too, right?
Yeah.
There's that spiral motion. So,
Wow.
how
Thank you,
lovely.
Diane.
I'm gonna stop here and maybe
I want to.
the rest of it.
Well, I need to follow up with a very basic question, and that is, those of us lay people that are following this story, what is the most significant discoveries so far from the days of Hubble till now? What are we finding? What's impacting us? I mean, obviously these images are showing a depth and to the entire universe that we've never had access to before. How does that affect us? What do we know? What is humanity going to be changed by all of this? What's the impact?
Why don't I let Tony answer that first, and then.
Well, I was going to ask, first of all, the impression of those here. Is it worth it? Are we happy that it was saved in 2011 to have this?
Yeah.
And that it wasn't canceled, right?
That it wasn't canceled.
Yes.
So the answer is yes, but if other people have comments on that too, I'd love to hear that.
Well, this is just the beginning, right?
It is just as Diana said, 2 months in,
Yeah.
we're just beginning to get data that's calibrated and can be interpreted, as opposed to the absolutely gorgeous pictures, much nicer than I'd ever expected. So
So it's performing
really
even better.
pretty excited about that.
Yeah.
And maybe I could just say that there's enough excitement that we're already planning the next one.
Yeah.
I commented that earlier, and
Can you give us a hint about what are some of the discussions with the next generation?
Yeah, to be aimed particularly at doing direct imaging of exoplanets. That's one of the big things that will be accomplished. Gopal mentioned terrestrial planet finder, which was a dream back about 2002 or so, and I was closely involved with that. And that was going great guns until all the money disappeared into another program called James Webb that was having overruns. And so that kind of ended the discussion then. And maybe that's a good thing, because we're so much more advanced in our understanding of how to do coronagraphs and how to implement large telescopes in space than we were at that point. But we're returning to that, and that came out of the National Academy of Sciences, the Astronomy 2020, which actually came out in November of last year, delayed due to COVID. And similar things are being considered on the European front too, looking at very large space telescopes and looking at exoplanets. And unlike Webb is the deep reach into the infrared, going way back in time. And there are other concepts that may do this on a slightly different scale than Webb, but the next great observatory will be looking into the ultraviolet in the visible part of the spectrum.
Okay.
But we're not going to be looking through dust the way we did before, but we're going to have aperture that will see things that we never saw in the past. And you may see pictures of not just exoplanets, but exo-Earths, which could be very exciting. So all that's coming. But again, it's not the pictures. It's going to answer these questions. I mean, some people say the biggest question of the 21st century is, do we know if we're alone or not? And we're doing exobiology. So we are tuning into something. We're honing in, and a lot of this comes from imagination and sense of what can be. You know, science is not a process of solving just solving equations. As Woody and Gopal and Diana will tell you, you all of a sudden you study a problem and you study it and you study it, and then you have a sense of how it has to be. And mathematics is a tool and a language we use, which is very powerful. But it's not that different than what we do on a more intuitive level as well. So, you know, where inspiration tends to come to us when we study something out, when we put the energy and time into it, when we open up those doors. So I see that as part of the science, and I see the rewards that come, which are very tangible.
Yeah.
John Mather, an associate of ours, who I think Woody, Paul, and Diana all know as well, has pointed out that what we're spending per year on Webb is equal to about 0.2%, less than 1% of what is being spent by the United States, by Europe, and by Japan in space every year.
Wow.
So 1/500th of the budget is going into this. Is it worth it to know all the secrets of the universe?
I'd say so. I have a question about the dark matter. So you're seeing its imprint. You're not seeing it, but you're seeing its effect. Is dark matter scattered everywhere, but just concentrated in areas? Or so it's really the matrix, one of the matrices of the universe. We're just seeing concentration. So it's everywhere. So
Go ahead. Sorry.
Are we ever going to develop an instrument that can see further into it, that detect it? Is there a bandwidth we're available to experiment with or to use technology for to reveal it? I mean, can we open up more bandwidth than we know about right now?
Yes, yeah, it's it wouldn't be exactly it wouldn't be necessarily searching for light they might emit at some wavelength.
Right. It's a different.
It's more indirect than that, but perhaps it still has a way to interact with regular particles. And then maybe the next step would be some light emitted or some type of a signal that instruments can pick up. But there are instruments being developed. It's a very active area of research. It sounds like you might want to talk with my partner, Francis Jan Siracine, who works not on the instruments, but he works exactly on dark matter, and he'd be able to tell you a lot more about what's going on there. He's not here right now, but
I'll tell him you volunteered him. So,
that's right. Oh well.
Yeah. You know, it's not about though that dark matter doesn't interact or does interact. It's like it's there. We're just not seeing its full capacity. We're not seeing its full influence.
It interacts, but four main forces, the four forces of the universe are the weak force and strong force, which are, we don't ever really have to deal with them in normal life. But then there's the electromagnetic force and the gravitational force. Those are the ones. The electromagnetic force is what causes, light to happen and how most particles interact and most matter interacts. And then gravity is another force that interacts. And of course, we also experience it. It doesn't emit any light, right? We know we're on Earth and not floating in space because of Earth's gravity. And this is also the main force through which we detect dark matter so far. We know that things in our galaxy orbit in a certain way that they shouldn't if all the mass present was all invisible matter, right? So the way that they orbit the center of the galaxy is weird. You can't explain it with just the mass in the stars that we see. Mm-hmm. There has to be more mass there to explain the speed at which they orbit and so on. And so that mass is dark matter, but we only know it's there and slightly indirectly because of motion of other objects that we do see around it.
Like watching the wheat in a field move, we know the wind is going through it. We don't.
Yeah, exactly. That's an excellent analogy. Thank you. Yeah.
Yeah, or that it's bending that light that we see.
Yes, that's another way. Yeah.
Like something, you put something in water and it's bending the light to our eyes. So it's a field that's
Gravitational field.
Mysterious field.
We also have black holes too, which we don't see directly, but we infer them from all the things that happen to matter around them.
That's right. Yeah, and the black holes are not dark matter. We think we understand
It's
where
distinct.
they come from.
Yeah, it's distinct. It's a whole another part of stellar genesis. But it's not the only manifestation. Even circumgalactic matter, it's very hard to see because it's extremely hot.
So black holes would have a lot more gravitational pull. So they're got gravity on steroids to start pulling.
Yeah. But gravity operates on different scales, and this is what Francis and Diana is referring to right now. Where a black hole is sort of a point. It's a singularity. It's
Well, we look forward to that.
Sounds like another
colleague and come back. Yes. Yeah, that will be fun. Thank you.
Well, I was going to ask Paul if he'd like to share any more, and then also Woody, of course. And so
well, while we get Woody back on, John Berger is asking, does the formation of stars and galaxies take longer now than 13 billion years ago? When is time changed, the nature of time? How would we know? We have nothing to measure against, do we? That would be a difficult question.
Yeah. So for galaxies, I would say yes. Some of the earlier galaxies formed very quickly. So one of the more spectacular results so far from Webb is perhaps not. Don't tell this to my exoplanet colleagues that I didn't choose the carbon dioxide as the most significant result. I'm sure there'll be more. But the fact that we're seeing galaxies younger than ever before, so at a time when we used to think the first stars were forming, we're actually seeing that galaxies already existed.
Okay.
The record so far from Webb is something like just over 200 million years old, and they're more massive. So the galaxies are bigger and more massive, really. They have more matter in them than we thought. They could that early after the Big Bang. So there was a higher speed of evolution of galaxies back then, yes. And then in terms of stars forming, star formation primarily depends on the amount of matter you have in a given place, and when you are able to get enough of that gas together for it to collapse into a star. So I think that's a little more dependent on the environment of each galaxy than on where we are in the age of the universe. So some galaxies have a lot of gas, dense gas. Stars will form faster there, and then other regions of star formation could be lower density and more spread out, and stars might form a little slower there.
But it's fascinating to think of a region of space where this is the nursery, this is the womb, this is where stars are birthed, and then they grow up, and then they go out do their thing, then they die. Children. I mean, they have a whole life cycle.
Of course, that nursery comes from a supernova, right? Which is a star that died. So all of its material blows off.
Yeah.
And all of that gas over time starts forming new babies, new stars.
It's recycled, right? It's the fertility that happens. It's going to give it that stuff of life. Oh, it's just fascinating. And then it ends up with us and living matter. Like, what an evolutionary arc.
Cycles of life.
Just so beautiful to behold.
Mm-hmm.
Wow.
Yeah.
And so here you are, the architects of the instruments to go seek these answers to the eternal questions.
Right.
Thank you. And I have to acknowledge the entire body of all the scientists and international
it's a huge team of
contributors to this.
And international cooperation. That's the other aspect to it, the international cooperation at a time when there's just not a lot of cooperation in the world. It's just wonderful to see, like, as a planet, can we work together as a planet on at least one project and not worry about who's going to, we hopefully Putin's not trying to design flags to place on each exoplanet as they, so.
We don't want to think that. But you mentioned another spacey kind of person is here too, and Michael Enoch. who has a lot to do with going to space and is
Oh, yeah.
engaged in something that Woody and Paul and I are involved in.
Yeah.
Oh, Michael Enoch, let's put all you on.
Yeah. Michael, would you like to
Gopal,
jump on,
if you want
please?
to
And
also
Kapal,
turn on
please
your
join
microphone
on.
or your camera. Yeah,
Yeah.
thank you.
Yeah, if you don't want to be on camera,
So
turn on your
glad your
mic.
colleagues have
Yeah.
joined in the
Yeah, yeah.
discussion.
Yeah,
So, are we going to put Michael Enoch
yeah.
on?
Michael
I
Enoch.
just saw the name right down there.
Yeah, okay. Yeah, but he hasn't turned on his mic yet.
From all spots, yeah.
Yeah, yeah,
Uh-oh.
yeah,
Oh, well, he got away with it.
yeah, yeah.
So you have to turn your cameras on, right?
Yeah, I
Or
can't-
speak up, turn on your microphones. We just want to congratulate you and thank you as well.
Yeah,
So,
yeah. Well, we appreciate it. Yes, exactly. So no one turned on the mics yet, but go ahead.
okay. Woody, we haven't heard from you in a few minutes, so we just want to,
Well,
ask you to chime in.
I'm not
what
quite
an
sure what-
undertaking. I know, let's just marvel at how extraordinary this is. What a beautiful time we live in.
I mean, stepping outside of your physicist brain for a moment, stepping outside of the numbers and the mathematics and all your entire lifetime of being devoted to this kind of work.
Yeah.
The human spirit seems to come to the surface. There's something greater being discovered and rediscovered here, possibly, and
it's
so
our
that's
curiosity
where
that's
you
driving
that's
us.
that's where you researchers are plugging into. You're bringing something back to humanity, and maybe, like I was saying a few minutes ago, we start thinking as a planet for a moment. Just for a moment, we can just think of ourselves as citizens of this one planet and not culturally.
Citizens of the cosmos.
And
Right?
then
This
the
is
next
our,
step.
This is our neighborhood.
Right, exactly.
And you're making it accessible.
So I put a
as
lot of
our
words in your mouth
neighborhood.
there, Woody, but yeah, what do you think?
You know,
Well, I'm not sure what to say. I do know that 1995 or 96, I was in Paris, and Bob Brown, a colleague, spoke, and he said we live in a unique time where we're investing dollars into these sorts of things, and it will not continue. It's new and it will not continue, but out of that we have learned so much about the universe and what the universe is and what it does. We basically use the technologies that are available to make measurements and we gather the data based on those technologies. There are cost limitations on what we can do, and I have personally to $10 billion is a lot of money.
Yeah.
And so I don't know where we go with that. There will be cost limitations, but it is exciting that we are able to do these things. So anyway.
Yeah, thank you
it's
so
exciting
much.
that you're already at
Yeah.
work. You all designing the next great telescope,
Yeah,
the tools of the future, and they have such a long time arc, 2.5 decades, right,
Yeah.
from conception
This
to
is-
deployment on average. Yeah,
Yeah, yeah.
means many lifetimes. Also, that you built on. I had to ask you one question. You know, the optics of the eye, right? And you talked about the pupil. Is there any relationship between what nature has designed for an eye and, the rods and the bouncing and this and what you're deploying? Our eyes are not made of mirrors, but you talked about pupils and
It's the same physics. It's the same physics. It uses the same mathematics.
wow. Maybe
You know,
so. Yeah.
the lens in the eye is made of different materials. The rods and cones that they detect light. We use electronics, silicon to detect or
As substitutes.
mercad, but it's the same physics. It's the same mathematics, and
yeah.
so anyway, yeah.
So this is one more step in the whole evolutionary journey that we can take what nature's devised and then we can imitate that in mechanical means.
And what eagles use every day.
Yeah.
Yeah. And
I just want to give nature a pat on the back too.
yeah.
Yeah.
And Michael Enoch said sorry he doesn't have his microphone and camera, but he did want to make the comment following up on what I said. He said Putin probably isn't, but the Chinese are. So
Yeah.
anyway.
That many people, you want to find land
And
for them, right?
John Berger asked a question. He says, are there kinds of galaxies? Are there any patterns in the distribution of galaxies? Patterns of galaxies.
Yeah, and I just said yes.
Yes.
It was a yes or no question.
Good answer. Good answer.
Yeah.
Anybody want to dispute it? No. Okay, move on.
Okay, here's my last question. Are there going to be new laws of physics that we can discover that we can deploy maybe? And how would we deploy them? Are there new laws of physics that we can do to really maybe get our planet back on track, to get our ecosystem back on track? Are we going to understand more about ourselves and life to do a better job caretaking the planet? Are we going to get ourselves out of this, mess that we're in with climate change?
Yeah.
Is this going to help on that?
It does,
What is our-
I can answer that question, yes.
Okay.
I was gonna say that's a good question, Laura.
Yeah.
Yeah.
I'm not so sure about new laws of physics. There might be, but there are new ways to deal with complexity that we've never had before.
Yeah.
For example, our ability to do weather forecasts. I can get a weather forecast for exactly where I live, or I'll be in a couple of weeks in Aix-en-Provence. I can find out exactly what the weather is there very easily with our forecasting tools. And this uses hundreds of thousands of data points and hundreds of thousands of equations in a way that it's called Bayesian mathematics, where you look at how the aggregate solutions come together. It's not quite as deterministic as me dropping this pencil to the tabletop. I didn't really drop it, but we would know exactly how long it would take, and we could do that to very great precision. But nevertheless, we can close in on problems with methods that we're developing to deal with complexity. At the same time, in our world, and you mentioned the problems we have to solve, complexity is something that's driving this in the wrong way. It's making it really hard for people to understand what's happening. When we have lawmakers that are making legislations that are thousands of pages long, with all sorts of earmarks, and then we expect them to be intelligently implemented, there are all sorts of things like that which we need to be aware of. So complexity is very much part of our world, part of the solutions in astrophysics, part of our solving the problems that we have going forward. Out of my swim lane here, but I couldn't resist.
And also not understanding the implications of everything that we do that has the ripple effect through environment and how complex it is. We don't understand the entire complexity. We need to understand we're all stakeholders in this future and everything that we're doing.
Yeah.
And to come together. I've wondered,
Maybe that's the
okay,
answer.
terraforming. If we are really looking at exoplanets, if we were looking to expand and plant our flag in another world, we would need to terraform it to some degree. But we are in effect terraforming unintentionally our own planet, right? Amping up Tony, you said if we're not careful, we'll end up with Venus here on Earth, that we're going to make it so hot. So if we understand terraforming, maybe we can terraform us back to the optimal habitable planet that we once were. We need to understand our effect and maybe how we can then tweak it to get back to where we should be. Is there any hope of that? Are there people are looking into that now? How to terraform a planet?
Well, obviously, we're looking at
Rise
ways
that to our own planet.
to reverse global warming.
Yeah.
This is something of concern. There are many solutions to that, and sometimes the approach that's taken is peculiar. Let me put it that way. On that, there are many factors that enter in, including global interest. And it's not like all the pollution happens right here, and there are things that are happening. Huge fires that happen in the rainforests that have great impact on it. There are things like that which are much more complex. They're international, and so I guess my sense is that we do need to look more clearly at what the answers are. And I'm not sure that California requiring only electric cars in 15 years is going to be the answer. It's obviously in a way along the path, But we have to look at this internationally. We have to look at this in every way we do. We have to look at what we're demanding of this. When I walk into a store and I see shells of water shipped in plastic bottles from Hawaii, I wonder what we're doing. There are things like that.
Michael Enoch, oh, I wish you'd turn on your mic. He's saying it's also probably worth pointing out that much of this technology is also useful for planetary defense to detect and possibly mitigate the threat that killed the dinosaurs. It would be incoming asteroids, low probability but high impact.
Yeah.
The other thing is the geopolitics. We mentioned when we talked about the international dark sky and all the threats to blocking our views of the stars with naked eyes, that the coming swarm of satellites would be simply because Europe has to have its set, the US to have its set, China wants its set, Russia wants its set. If we all got along, we could have much less technology if we could all share equally.
Everybody in the world needs everybody in the world needs high-speed gaming. I mean, really.
At any cost,
Get
right?
real,
Any
Laurelie,
cost.
get real.
But is science? Are these telescopes? Are you above the fray of geopolitics in the field of aeronautics?
Not in the least bit. And this is something of concern even before we were talking about laser communication and 5G from space and things like that. It was a great concern. The number of satellites we put up there, those that occasionally blow up. We had that happen in China recently. They cause all sorts of pieces of stuff there. There are a lot of things that are of concern that we all do, and it's we need to take responsibility for it. Webb is very far away, as Woody said, 1% of the distance from the sun to Earth, but that's very far away, and that's probably not going to impact the Earth in a significant way. Whereas Sputnik, things that will orbit the Earth several times a day, it's of concern, and we need to be aware. I like the way Michael said planetary defense, and this is something that is important, both from asteroid impact, but we also have to consider, the amount of space junk and what's going to happen to that.
Yeah.
It's just ironic that you are part of a team, international team, to expand our bandwidth, to understand and lend greater acuity, greater distance, greater understanding of the stars. At the same time, we're looking to block our view of the stars. On a naked eye view of the stars. It's kind of ironic.
This is in part not complete thinking, the law of unexpected consequences.
Right.
All sorts of things. We talked last week about how diode lighting for streets and houses and stuff like that is much more efficient. However, the light, unless you do something about it, is a lot bluer. And so you may think you're saving the planet by using less efficient lights, but maybe you're just making brighter lights that shine far more in the blue and cause more scattered light. And so we lose our ability to see stars.
Barentine showed that 2 examples of overlighting your security driveway, and you couldn't see the person behind the fence. When you dim it down, rather like you're dimming down the stars with the filters, corona filters, then you can actually see better. So it's kind of the same principle. But I want to say that our emotional relationship with the cosmos that has steered humankind from time immemorial, that is so worth protecting. I hope that we never get to the point where we're only relying on these images from these telescopes to give us that sense of the stars and our access to them. I hope we don't get so. I think it's brilliant. It's important to have, but it should not be our only view. We need to protect that view that we've enjoyed from the get-go of the dark sky and all of its myriad stars.
And possibly this is the ultimate environmental project. Protecting the planet.
Saving the planet.
It's the whole big picture thing. And maybe coming back to my question 30 minutes ago, and that idea about how we as lay people can grasp what's happening, what we can learn from all this, and how this is all going to affect us. Maybe just that concept that we're one planet, people, and the only way we're going to make this thing is together. And maybe just by the fact that we can look out and look back at ourselves and say, what the hell? What an amazing thing we have here.
One
Why
little
are we
tiny
such idiots?
fragile blue
Stop
dot.
being such idiots.
Spaceship Earth. Yeah.
Possibly.
Yeah. Thank you all for all the work
Yeah,
that you're
thank you.
doing.
Yeah,
Appreciate
absolutely.
it. And
Yeah.
And thank you, Gopal and Michael Enoch and others
And all
who are
of you
working in
that
this
have joined
sector.
us today. So what a fantastic
celebration.
way. And
We're just like
continue-
applauding you
and-
all.
And I'm sorry. James Webb is going to have new stuff every single week. So I would be watching the news, watching the images, watch the research.
Where's the best website? Where's the best website?
Well, it's
to
a place
tune
called
in?
NASA.
Subscribe.
Yeah.
Yeah.
But it's in the news. Right.
Yeah,
What do you go to follow the news each day to see what's going on?
Twitter.
Twitter. Yeah. Yeah. All right.
Sorry, not very helpful. And then I click from there.
Yeah,
Yeah.
absolutely. All right.
Thank
Well,
you.
blessings to you all. Thank you so much for being here. And before I hang up here, before we turn it off, let's go ahead and ask everybody, because the community has stayed here for a long time and want to hear the entire presentation. And so I'm going to ask
I'd like to thank everybody that tuned in and Paul and Laura for this. It's wonderful to be able to talk in this very open way, more from the point of view of heart than hard science. Really appreciate it.
Thank you, guys.
Thank you all for being here.
Thank you.